Hello, good evening. I am Saurabh and I welcome all of you to this live session for the NPTEL course IC Engines and Gas Turbines. This is our session 12 and as you know that this was a 12-week course. So this is last regular session, but we are also planning to take one extra session and the schedule of that extra session will be communicated to you via email. So in week 12, the topic of discussion was mostly nozzles and diffusers. So in this session, we will try to solve some problems related to nozzles and diffusers. So nozzles and diffusers. So as you know, that purpose of nozzle is to increase the kinetic energy, or velocity, and purpose of diffuser is to increase the pressure. Okay. So when you want to increase the kinetic energy, when you need thrust, right? So for example, in turbojets, you want thrust, right? But in power plants, your purpose is to rotate a shaft and you want some torque. But in aviation, in jet applications, the purpose to get the thrust. Okay. So to get the thrust, you want to increase the kinetic energy of your exhaust gases. So for that purpose, you are using nozzle. And purpose of diffuser is to increase the pressure. Why? Because you want to compress the gas and that compressed gas will be sent to combustion chamber, right? So to reduce the compression work, what you do, you increase the pressure of incoming air by using some arrangement that is diffuser. Okay, so that the work input to compressor can be reduced. Okay, so with this background, we will start our discussion. So question number 1 says the primary function of intake used in any subsonic aircraft engine is to. Okay, so intake. So diffuser is used at intake, right? So first of all, there will be some air coming in, right, at intake. Then there will be diffuser. Okay. Then there will be diffuser. So this diffuser will increase the pressure of this incoming gas. Then it will go through compressor. Then there will be combustion chamber. And then there will be a nozzle, right? Nozzle, or before nozzle, you can make a turbine, right? Turbine. Why turbine? Because you want to rotate this compressor shaft. Okay. And to for compressor, you need some work output and that work, you want some work input and that work input will come from the turbine work output. Okay. So you also have turbine. Anyways, it is saying the primary function of intake. So intake here basically intake means this diffuser part. Okay. This is at intake. So it is asking about diffuser used in any subsonic. So subsonic means when the velocities are less than Mach number 1. Okay. So it is not near to Mach number 1. So it should be, so velocities will be less than 0.8 c, something in that range. Okay. So when the velocities are comparable with the speed of sound, then compressible effects also comes into the picture. So but here it is subsonic. Okay. So the velocities are less than 0.8 Mach. function of the intake it is asking. So option A says to increase the kinetic energy of the gas as it enters the engine. Option B, it says increase the pressure of the air as it enters the engine. Option C says to improve the turbine work output. Or option D, to diminish the strength of the shock on the compressor blade. So it is asking about the primary function of intake. So that means the primary function of diffuser. So as we discussed just few seconds ago, that the purpose of diffuser is to increase the pressure, right? So purpose of diffuser is to increase the pressure. So you can easily answer this question, and as you must have guessed that the correct option is the option B, to increase the pressure of air as it enters the engine. Okay, so this is the primary purpose of the diffuser. Doesn't matter whether intake air is at subsonic regime or it is in supersonic regime or any regime. The purpose of diffuser is to increase the pressure. Okay, if the flow is in some other regime, if it is in subsonic or in supersonic, then the design of diffuser can change. It can be converging or diverging or some other special design, but the main purpose remains the same. The main purpose is to increase the pressure. Okay, so if it is clear, then we can move to the next question. Question number 2. Question number 2 says, for the subsonic flow through a nozzle, how do pressure and velocity changes as the fluid flows? So now it is in the supersonic flow. Okay, supersonic flow means Mach number is greater than 1. Okay, through a nozzle, how do pressure and velocity changes as the fluid flows? So again, doesn't matter whether it is supersonic or subsonic or hypersonic, whatever. The purpose of nozzle is what? Purpose of nozzle is to increase the kinetic energy. The purpose of nozzle is to increase the velocity, right? So it is asking how the velocity will change when the fluid passes through the nozzle. So you can blindly answer that velocity should increase. So let us see all these options. Option A says pressure increases and velocity decreases. Of course, it is not correct. Option B, pressure increases and velocity remains constant. Option C, pressure decreases and velocity increases. Yes, velocity should increase. And option D says pressure remains constant and velocity increases. So you also know that velocity is increasing and pressure is decreasing. Okay, pressure does not remain constant. Okay, so there is some pressure drop in the nozzle. There is expansion. Okay, the correct option is option C. Velocity increases and pressure decreases. Okay, so still we have not said anything about the diverging nozzle or converging nozzle or any design aspect. We are simply talking about their purpose. The purpose of nozzle is to increase the velocity. Okay. I hope it is clear. If it is clear, then we have question number 3. Question number 3 says, in a scramjet engine, air enters the intake at blank space speed and undergoes combustion at some speed in the combustion chamber. So basically we have to find which word should be filled at this blank space. So in scramjet engine, so you know what is scramjet engine? So scramjet basically stands for first of all, I hope you know what is ramjet engine, right? So as the name suggests that in ramjet engine, you are using ram effect. Okay, ram effect for compression. So what is ram effect? Ram effect is basically taking the advantage of moving air. Okay. So moving air means the air is coming inside and it has some momentum, right? It has some momentum. And taking the advantage of that momentum, you can design your engine in such a way that without using any moving part, without using any rotating part, just using the design, this air can be compressed. Okay. Why? Because it has some momentum and if you have some special design, then this gas can be compressed. Okay, so for exact design, you can refer any textbook or any good source. But the thing that you should understand here is that ram effect means taking the advantage of momentum of the moving air to compress this air. Okay, so that is ram effect, and ram effect is used in engines. Those engines are called ramjet. So in ramjet engines, you don't have any compressor, so you don't have any rotating part, you don't have any moving part. Okay, so that is advantage. And then of course after compression, this air will reach into the combustion chamber, their combustion will happen, and then air will expand and you will get the thrust. Okay, but it is asking about combustion. Okay, combustion and intake. Okay, so at intake it is at supersonic speed. Okay, it is at supersonic speed. Why? Because here you are not using any compressor, you are not using any mechanical device to compress this air, you are only using the thermodynamics to compress this air. And that thermodynamic process is basically compressibility or the shock generation. Okay, so the air, since it is at in the supersonic regime, at intake supersonic regime, so it will generate some shock, and because of that air will be compressed. So at intake, air enters at supersonic speeds. Supersonic means the speed is greater than the speed of sound. So Mach number is greater than 1, supersonic speeds, and undergoes the combustion is at subsonic speed. Okay, so after this compression, after this compression, when this air reaches the combustion chamber, then the air speed has been reduced to subsonic regime. Okay, so the combustion happens at subsonic, not at supersonic. So in scramjet, the combustion happens at subsonic regime. Okay, so option A says supersonic intake and subsonic combustion. Option B says subsonic intake, supersonic combustion, and so on. And yeah, you know that the correct option is option A. Air enters intake at supersonic speed and undergoes combustion at subsonic speed. Okay. There are another type of engines which are called scramjet. Okay, sorry. This question was about scramjet engine. This question was about scramjet engine. So scramjet basically means so in scramjet you can see the ram. So ramjet word is there, right? So ramming effect is there, but this SC stands for basically supersonic combustion. Okay, supersonic combustion, supersonic combustion. Okay, everything is same, but combustion happens at in the supersonic regime. Okay, so this is the difference. In scramjet, combustion happens at subsonic regime, and in scramjet, combustion happens at supersonic regime. So supersonic. So in scramjet engine, air enters at supersonic speed, and combustion is also at the supersonic speed. So both are supersonic. So option D is the correct option. Okay. If the question was about ramjet, then correct option would have been option A, right? I hope it's clear. Coming to the next question, question number 4. Question number 4, it says which statement is correct about a ramjet? Okay, so now we have a ramjet engine. Option A says the flow enters the engine with subsonic speed and undergoes the subsonic combustion. So the question is what we discussed in the previous question, right? And option B says flow enters the engine with the subsonic speed and undergoes supersonic combustion, and so on. And the last option says flow enters the engine with supersonic speed and undergoes subsonic combustion in the combustion chamber. So now you know that at intake, flow enters at supersonic speed, right? Ramjet engine. and combustion, it is at subsonic speed. So which option should be the correct option? Air enters with subsonic speed? No, wrong. Option B, air enters at subsonic speed? No. Flow enters engine with supersonic speed? Yes. And undergoes subsonic combustion? Yes, this is correct. And option D says flow enters the engine with supersonic speed and undergoes supersonic combustion. This is not correct. Or ramjet, flow enters engine with supersonic speed and undergoes subsonic combustion. Okay. So coming to the next question, question number 5. It says which statement is true for the fluid flow through a diverging duct? So diverging duct basically means that you have some duct and area of cross section of that duct, it is increasing. Okay. So this cross section area, if it is A1 here, A2 here, then A2 is greater than A1. So the cross section area is increasing, and this is called diverging duct. Okay. It's called diverging duct. So which statement is true for diverging duct? So we have four options. Option A, always functions as a diffuser, which is independent of inlet Mach number. So it is saying that if you have this type of diverging duct, then it will always act a diffuser and it is independent of inlet Mach number. So this is correct or incorrect? We will see what is the effect of Mach number, but let us read all these options. Option B says functions as a nozzle only if the inlet flow is subsonic. Option C says acts as a diffuser only if the inlet flow is supersonic. Option D says functions as both nozzle and diffuser depending on the inlet Mach number. So there is a relation involving the Mach number. So there is a relation involving the Mach number. I will write this relation that has been discussed in the lecture. So that is dA. So area, sorry, A is basically the cross-sectional area. dA is equal to m square minus 1 dV by V. Okay. So A is the cross-sectional area, m is the Mach number, V is the velocity. Okay. So now we can answer this question. So let us take all the possibilities. So we will first check subsonic. Or Mach number is less than 1. So what will happen when the Mach number is less than 1 and the flow is in the subsonic regime? Then you will have m square minus 1. So this will be greater than 1, right? Okay. So if you see this equation, then this term will be positive, right? Am I right? Okay. So this is not correct. Why it is not correct? This is not correct. I have written here that in subsonic regime, Mach number is less than 1, right? In subsonic regime, Mach number is less than 1. What is Mach number? Mach number is the flow velocity divided by the sound velocity. This is Mach number. In subsonic regime, the speed is less than sound speed, and Mach number is less than 1. So if m is less than 1, then how m square minus 1 can be greater than, sorry, 0, greater than 0? If m is less than 1, then m square minus 1, this will be negative, right? This will be negative. So this will be negative. Why? M is less than 1, so m square minus 1 will be negative. So this means that if dA it is increasing, then dV, sorry, if the A is decreasing, if the cross-sectional area is decreasing, if dA is negative, then dV will have to be positive, right? If cross-sectional area is decreasing, then velocity will be increasing in subsonic regime. Okay, for the subsonic case. Okay, so if area increases, then velocity will decrease, and if area is decreasing, then velocity will increase. So this is for the case of subsonic. Now what will happen for the supersonic? For supersonic case, Mach number is greater than 1. So this term m square minus 1, this will be positive. Okay, so from the same relation, you can say that if area is increasing, then velocity will also increase. If area is decreasing, then velocity will also decrease. This is for supersonic case. Okay, so these are all the possibilities. Now you can answer this question. It is saying diverging duct. So diverging duct means area is increasing. Okay, diverging duct means area is increasing. So dA by A, it is positive. Now let us check all these options again. Always functions as a diffuser which is independent of inlet Mach number. So this is not correct, right? Why? Because it is dependent on the Mach number, right? It's dependent on the Mach number because we have seen two cases, whether it is in subsonic regime or it is in the supersonic regime. So whether it will act like a diffuser or it will act like a nozzle, that depends on the inlet Mach number. So for this duct to act like a nozzle, the velocity should increase. Okay. If the velocity is increasing, then it is nozzle. Otherwise, it is diffuser. Okay. And this is in the subsonic regime. For supersonic regime as well, if velocity is increasing, then it is nozzle. Otherwise, it is diffuser. Okay. And since the area is decreasing, so this case, this is the case, right? For supersonic regime, this diverging, sorry, area is increasing. It is diverging duct. So for supersonic regime, this will act as a nozzle, but for subsonic regime, this will act like a diffuser. Okay. But here it is saying that it is independent of Mach number, so it is wrong. Okay, so it can act like a diffuser as well as nozzle depending on the Mach number. Options B says functions as a nozzle only if the inlet flow is subsonic. So if the inlet flow is subsonic, then for diverging duct, this will act like a diffuser. Okay, so this is also not correct. Okay, this will not act in nozzle. It will not function like a nozzle if the inlet flow is subsonic. Option C says acts as a diffuser only if the inlet flow is supersonic. So this is correct, right? So for supersonic regime, if it is a diverging duct, if area is increasing, then Then if area is increasing, then velocity will also increase, then it will act like a nozzle. Sorry, here it is saying diffuser, so it is also not correct. Okay. Option D says functions as both a nozzle and a diffuser depending on the inlet Mach number. So this is the correct option, right? So this is the correct option. Okay. If the inlet flow is supersonic, then diverging duct will act like a nozzle. If inlet flow is subsonic, then this diverging duct will act like a diffuser. So it can act like a diffuser as well as nozzle depending on the inlet Mach number. So option D is the only correct option. Okay. So this is a very important relation. Okay. So this you should keep in mind. Okay. So is there any doubt? Okay. I think it is clear and we can move to the next question. Question number 6. It says that in a converging duct with supersonic inlet flow. Okay. So now Mach number is greater than 1. The pressure, and we have to fill in this blanks, while the velocity, again some blanks, along the length of duct. So it is asking what will happen to pressure and velocity along the duct when we have supersonic inlet flow. Okay. Supersonic inlet flow means Mach number is greater than 1 and it is converging duct. Converging duct means area is decreasing. So dA by A, it is negative. Okay. So again, you can use the same, relation. dA by A, that was equal to m square minus 1 dV by V, right? And it is converging duct. So this term is negative. This term is negative and it is supersonic. So m is greater than 1. So it is positive. That's why this dV by V will have to be negative. Okay. This will have to be negative. So this means velocity will be decreasing. So it will act like a diffuser. Okay. So in diffuser, as you know, that pressure increases and velocity decreases. Okay. So now you can easily answer this question. In a converging duct with a supersonic inlet, the pressure will increase and velocity will decrease. Pressure will increase and velocity will decrease. So option A should be the correct option. Okay. Okay. Now we have question number 7. It says the flow through a nozzle is classified as under expanded when the nozzle exit pressure is. So as you know that in nozzle, basically speed is increasing and expansion is taking place, right? Pressure is continuously decreasing. It is an expansion process. And okay, let us say this is a nozzle. Here you have some pressure P and outside you have some pressure, ambient pressure. This is pressure at inlet and this is pressure at outlet. Okay. So this Pi, this is greater than P ambient. Okay. And it will be continuously decreasing. So Pe will be less than Pi. Okay. it will be continuously decreasing. But at outlet, if whether this P exit is less than or greater than P ambient, based on that you can say whether it is overexpanded or underexpanded. So underexpanded means the expansion has not been enough to decrease this pressure up to the ambient pressure. Okay. And over expansion means it has been, expanded more than, it has been expanded up to, it has been expanded up to such limits so that this pressure at exit, it is, it is less than the ambient pressure. Okay. But here it is asking about under expansion. So it means this P exit is still less than, sorry, it is still greater than ambient pressure. Okay. So this is under expansion. If this would have been overexpanded, then this will have been decreased even less than even ambient pressure. Okay, so this will be overexpansion. Okay, here it is asking about under expansion. So nozzle exit pressure, this will be lower than the ambient pressure? No. Higher than the ambient pressure? Yes. Equal to the ambient pressure, equal to the reservoir pressure? No. So it will be higher than the ambient pressure. Okay. So this is what we mean by over expansion or under expansion. Okay, I hope this is clear. Okay. So if there is any doubt, then please ask. If there is no doubt, then we can move to the next question. Okay. Okay. So question number 8. It says that for a given reservoir temperature and pressure, the flow at the minimum cross-sectional area of the choked convergent divergent nozzle is expected to be. So you have studied about convergent and divergent nozzle, CD nozzles, right? So as the name suggests that first there will be convergent part and then there will be divergent part. So convergent part means the area will be cross-sectional area will be decreasing. Okay, cross-sectional area will be decreasing. Then cross-sectional area will be increasing. Okay, so this first part is convergent part and this part is divergent part. Okay, so it is asking about flow at minimum cross-sectional area. So here you have the minimum cross-sectional area. Okay, so this part is the minimum cross-sectional area. And in case of a choked convergent divergent nozzle, the Mach number at this, at the minimum cross-sectional area point, this should be equal to the Mach number is equal to 1. Okay, this should be equal to the speed of sound. Okay, so here you should have Mach number is equal to 1. Okay. So Mach number 1 means it is subsonic, no. Supersonic, no. Hypersonic, no. It is sonic. Okay. And why we have these type of special shapes, that can be explained by the equation that we have discussed in the previous question, right? The effect of Mach number. Okay. So depending on the Mach number at this point, whether this Mach number is greater than 1 or equal to 1 or, or less than 1, the behavior of the working of this convergent part and divergent part will be different. Okay. So I hope this is clear. But one thing you should note here is that this equation is very important, right? So many questions can be answered just by this simple equation. Okay. So again, CD nozzle. Okay. So question number 9 says, in a CD nozzle, what is the characteristic of the throat section area? So throat section area is basically that minimum cross section part. Okay. Minimum cross section part. Let us see all these options. Option A says it is the region of maximum expansion. It is the region of minimum cross sectional area. Yes, it is correct. It is the region where subsonic flow is achieved. So this is not correct, right? It can be supersonic or subsonic, or even for choke condition, it can be equal to 1. Mach number can be equal to 1. And option D says it is responsible for heat dissipation. No, it is the part where the cross sectional area is minimum. Okay, so the only B option is correct. Okay. This is throat area. Okay. I hope this is clear. Now question number 10. It says which expression among the following gives the correct area Mach number relation for varying area duct. So this we have discussed many times, right? Where V is velocity, dV is change in velocity, A is the area of duct, dA is the change in area, and M is the Mach number. So now I want you to please answer which option is the correct option. We have written this many times. Which option is the correct option? Hello, you can unmute yourself and speak. I think Mayank want to say something. You can write in the comment section. This is the last question. Vishnu, you want to answer this? This is not a question. This is just, we have written, I think, I didn't even count how many times I have written this. Okay, so here it is. dA by A is equal to m square minus 1 dV by V. Okay. So which one is correct? Option A, dA by A is equal to 1 minus m square. No, it is not correct. It is actually m square minus 1. Option B says dV is equal to 1 minus m square. No, again, this is not correct. Option C says dA by A is equal to 1 divided by m square minus 1. This is not correct, right? This is 1, sorry, m square minus 1. It is not in the denominator. Option C says dV is equal to this thing. Yes, this is correct, right? Because these both are same. Okay. So option D is the correct option. Okay. This is important relation, I think. because it explains many phenomena for the nozzles diffusers, right? So this was the last question from this session, and this is the question from previous session. Because of limited time, we did not solve this question. So today we have some remaining time, so we can solve this, right? So the question says airflow from atmosphere at pressure 100.3 kilopascal and temperature 288 Kelvin into a centrifugal compressor. Okay, so you have a centrifugal compressor with the radial blades at exit of impeller. So it means at the impeller blades are radial, right? So blade angle at the exit of impeller is 0, right? So beta 2 is 0, and without any swirl at inlet. Without any swirl at inlet means there is no whirl velocity component at inlet, right? And then it says the compressor wheel has 18 blades and it turns at 15,000 rpm. So this is your omega. The exit radius R2 is equal to 26 centimeter and the inlet hub radius is 8.5 centimeter and the shroud radius is 17 centimeter. The total to total efficiency is 0.79. We have to find the power required. Why power required? This is a compressor, and compressors are work consuming device, power consuming device. So it will consume some work. So power required, assuming that mass flow rate m dot is 8 kilogram per hour. Use the Stanage formula to find the slip coefficient. Find the stagnation pressure ratio. Okay. So all these terms, if you don't know any term, then we can of course discuss this. Okay. So now we will try to solve this problem. Okay. So it is saying that air is coming from the atmosphere, right? And you know that in the atmosphere, it is in the rest condition. It is in the stagnant conditions, right? So inlet stagnation properties are atmospheric properties, right? So at inlet, atmospheric pressure and atmospheric temperature, that will be your inlet stagnation properties, right? Stagnation temperature will be 288 Kelvin and stagnation pressure that will be equal to 101.3 kilopascal. And you know what are stagnation properties? So stagnation basically means when you bring the fluid to the rest isentropically, and if you bring the moving fluid to the rest isentropically, then properties of fluid at rest, those properties will be your stagnation properties. Okay, fine. Hello. Okay. Now let us find the blade velocities. Okay, blade tip velocities or the tangential velocity, right? U. Let us find the U. So blade tip velocity is equal to omega times radius, right? Hello. So first, I think I should make a diagram. So this is your blade. If it is, backward facing, then it will be something like this. And it is saying that it is radial at impeller exit. So actually it should be something like this. Okay. Anyways, we will see. So blade tip velocity is omega times r, and omega it is given to be how much? 15,000 rpm. So this means 15,000 times 2 pi radian per minute. Per minute means, sorry, per second means that you have to divide by 60, right? This is per minute. So this will be in radian per second. Okay. Hello. So blade tip velocities will be u2 will be equal to radius at outlet times omega. And what is radius at outlet? Exit radius it is given to be 26 centimeter, right? So it will be 0.26 meter times omega is 15,000 times 2 pi by 60, right? This will be in meter per second. If you calculate this, then 0.26 times 15,000 times 2 times pi divided by 60. Okay, so this is 408.4 meter per second. Okay. Similarly, at other points, you can find this blade velocity. Okay. At shroud radius, you can find this value. So this will be Rs times omega. And this is shroud radius is 17 and hub radius is 8.5. Okay. So at all these points you can calculate, and mean, where is the mean? Mean was also there, right? Anyways. So at shroud, it will be 0.17 meters times 15,000 times 2 pi by 60 meter per second. So this is tangential velocity at, or the blade velocity at shroud. I am writing the direct values because I already have the answers. Okay, you please try to calculate yourself and check if it is any problem. And at hub, this is 80 8.5. So 0.085 times 15,000 times 2 pi by 60 meter per second. So it will come out to be 133.5 meter per second. Okay. Okay. So now coming to the outlet. At outlet, you know that in ideal case, the velocity at outlet is equal to is equal to the blade tip velocity, right? In ideal case. Hello? Okay, let me make the diagram. So in the ideal case, for the radial blades, this is outlet, and this is the tangential velocity or the blade velocity. So this is equal to u. Okay, this is equal to u, and radial velocity or this relative velocity, this will be along the blade. So this will be relative velocity. So we will make this is v. Okay, this is v. So better I make u that side, another side. This is u, this is v. So this will be absolute velocity. This will be absolute velocity c. Now if you see that this component and this component, so this is basically will component of velocity, and this is radial component of velocity. Okay, so from here you can see that radial component of velocity is equal to relative velocity v, and viral component of velocity, it is equal to u. Okay, but this is in the ideal case. In actual case, this viral velocity is not equal to your blade velocity. Okay, so this is not, these are not equal. So this difference or this ratio, that is called the slip factor. Okay, that is called slip factor or the slip coefficient. So slip coefficient is defined as sigma. Sigma is actually your actual CV, okay, divided by u. Okay, so this is slip coefficient. And there is a one empirical relation that is called Stanage formula. Okay, so Stanage formula basically is a relation for slip factor in terms of number of blades. So that is equal to sigma is equal to 1 minus 0.63 times pi by n, and n is the number of blades. Okay, so in our case, n is equal to n18. N is equal to n is equal to 18. So sigma will be equal to 1 minus 0.63 times pi divided by 18. Right? 18 is given in the question. It is given that compressor has 18 blades. So it is given in the question that compressor has 18 blades. So n is equal to n. So from here you can calculate the sigma. Okay. So from here you can calculate the sigma. Sigma will be 1 minus 0.63 times pi divided by 18. Okay, so this is coming out to be 0.89. So this is slip factor, right? So this is slip factor. Okay. So it was given in the question to use the standard formula to find the slip coefficient, okay, or the slip factor, whatever. Okay. What else? Let me erase these things. Okay. Now it is saying that without any swirl at inlet. So without any swirl at inlet means there is no whirl component of velocity, right? So all the flow is in the axial direction, right? Inlet flow is in the axial direction, right? So since flow is axial at inlet, so you can write work done, right? You can write work done. This is not omega, this is work done. This will be equal to, this will be equal to what? CW2 U2 minus U2 into U2, CW1 times U1, and this term is 0, right? So work done will be only CW2 times U2, right? Is this clear? This formula I hope you know this, right? Okay, anyways, I hope this is clear. If there is any doubt, then please ask. Okay, and CW2, this you can calculate from the slip coefficient, right? You can calculate from slip coefficient, because CW2 will be given as sigma times U2, right? Sigma times U2. This is the definition of slip coefficient. So work done you can write in terms of slip coefficient as sigma times U2 times U2. So it is basically sigma times U2 square, right? And sigma you just calculated from Stannis formula. This is coming out to be 0.89 times U2. U2 is the blade velocity at exit. So what is blade velocity at exit? That we calculated in the beginning itself. So blade tip velocity at exit, it is 408.4 meter per second, right? So 408.4, 408.4 squared. Okay, so this is the work done, kilojoule per kg. Okay, so this is per kilogram. This is small. This is specific work input. So this is small w. Okay, so the power input to the compressor will be what? This is per kg. This is per unit mass. So power input to the compressor will be mass flow rate times specific work input, right? So this will be, and if you calculate this thing, then it will come. I already have the value, so I'm writing it directly. So it is coming out to be 148.46 kilojoule per kg. You please calculate yourself, and if there is any difference, then please let me know. Okay. So this you can write as mass flow rate was 8 kilogram per second. This was given in the question. This was given in the question. So here it is given that mass flow rate is 8 kilogram per second. Okay. So 8 kilogram per second times this specific work input. 8 kilogram per second times 148.46 kilojoule per kg. So now again, if you calculate this value, then you will get power input to the compressor. You can calculate this value, and I hope that this is not that you get these values 1187.6 kilowatt or kilojoule per second. Okay, so please check these calculations. If there is any mistake, then please let me know. Okay. So this was the first part of question. This was the first part of question. Power required we had to calculate. So power required we had calculated. Mass flow rate was given and Stein's formula we used to calculate the Seebeck coefficient. Now we have to find the stagnation pressure ratio. We have to find stagnation pressure ratio. So what is stagnation pressure ratio? Now you have to find second part. Stagnation pressure ratio. So pressure ratio is defined by P2 by P1, right? P2 by P1. But stagnation pressure ratio is defined by P naught 1 by P naught, right? So it is not same as P1 and P2. It is actually P02 by P01. Okay, right? But pressure, to find the pressure, we can use the temperature. So first of all, I think we can calculate the temperature. So how will we calculate the temperature? So since isentropic efficiency is given, right? So this efficiency is given, total to total efficiency 0.79. So that I think we can use that, right? So isentropic work. So isentropic work will be less than the actual work, right? Isentropic work will be less than actual work, because in actual work you have to provide some more work input because there are some losses. But in isentropic case there is no losses, so that work is uh, less than the actual work. So that is basically the definition of efficiency. Actual isentropic work by isentropic work divide by actual work. That is your efficiency. Okay, and actual work you have just calculated, right? You have just calculated per unit mass basis. It is 148.46. Okay, so isentropic work you can write it as isentropic work, or again this is per kilogram basis. So this will be neta times actual work. So actual work is how much? 148.46, right? 148.46 kilojoule per kg. And this efficiency is also given in the question, and that was 79%. So 0.79 times 148.46 kilojoule per kg. So this will be your isentropic work. And if you calculate this value, then this will come out to be, I am writing the value directly, 117.3 kilojoule per kg. So this is the isentropic work. Okay, this is the isentropic work. And isentropic work, isentropic work is equal to Cp times delta T, right? Cp times delta T. So delta T you can find as Ws by Cp, right? And this will be equal to 117.3 kilojoule per kg. And Cp, it is not, I think, not given in the question, but you can assume this to be something around 1.004. Okay. Kilojoule per kg Kelvin. Okay. So I am assuming this value. Okay. So the temperature at exit will be the stagnation temperature at exit. Exit T2, or rather I should write T02. That will be equal to temperature at inlet plus delta T. Okay. And at inlet, this was how much? This was given to be the atmospheric temperature. How much was the atmospheric temperature? This was 288 Kelvin. 288 Kelvin plus this temperature rise, 117.3 kilojoule per kg divided by 0014 kilogram kilojoule per kg Kelvin. Okay. So this T02, this will come out to be 404 point. I'm writing the direct values. Please check the calculations. Okay. So this. Okay. Now from your isentropic relation or adiabatic relation, you can write the pressure ratios as P. Sorry, what you write P2 by P1, that is equal to P2, sorry, T2 by T1 to the power gamma divided by gamma minus 1. And similarly for as stagnation conditions also you can write as P02 by P01 will be equal to T02 by T01 times, sorry, to the power gamma to the power gamma by gamma minus 1. Okay. And P02 you have just sorry, this is the stagnation pressure ratio that you have to calculate. Stagnation pressure ratio. And T02 you have just got, it is 404.78, and T01 was 288 Kelvin. To the power gamma, let us assume 1.4. Okay, 1.4 divided by 1.4 minus 1. Okay, so again, if you calculate this value, this is coming out to be like this. And let me cross check. 1.4 divided by 0.4. So this will come out to be 3.29. Okay. So P02 by P01, this is equal to 3.29. So this is your stagnation pressure ratio that you had to calculate. That we had to calculate. Okay. So yes, so stagnation pressure ratio is, so I should write the answer, I think. Answer sigma we calculated and it came out to be 0.89. Okay. And power required we calculated to be 1187.6 1187.6 kilojoule per second, and stagnation pressure ratio, this is 3.29. Okay, so we have found, we have got all these values. One thing I would like to emphasize in this question is that these velocity diagrams should be very clear. Okay, these velocity diagrams should be very clear. Sometimes it is given that it has no whirl, it has no swirl. This is the blade angle at inlet, this is the blade angle at outlet. Okay, so from which direction these angles are being measured, that is very important. Okay, so from axial direction or radial direction, or the from the flow direction, or the directions are very important. Okay, because if these things are not clear, if these directions, these angles are not clear, then definitely we cannot make the correct velocity triangles. And if the velocity triangles are not correct, then we will uh, led to the incorrect values. Okay, so few things that you can keep in mind is that the relative velocity that is along the your blade. Okay, so here if this is the blade, I am showing you the first picture. So if it is, this is the blade, this is the blade, then relative velocity will be along this blade. Okay, this will be along this blade. V will be along this blade, and the blade tip velocity that we call tangential velocity, that will be along this, you know this hub. Okay, since this whole thing is rotating, rather I can make the smaller version. Okay, so and this whole thing is rotating, this is like a circle. Okay, okay, So this whole thing is rotating about the center omega, and this radius is r, and the u, that is tangential velocity or blade velocity, that is actually along this circle, okay, that is tangential velocity tangent to this circle, okay. And the absolute velocity, that is equal to the absolute velocity is equal to the blade velocity or the tangential velocity plus relative velocity, okay. Okay, so if I make, so this is the absolute velocity, this is the absolute velocity, that is the resultant of u and v. Now this absolute velocity can be resolved in two components. This can be resolved in two components. One component will be in along the direction of this blade velocity, okay. So one component will be along the blade tip, okay, along the tangential component. So component which is, sorry, so the component which is along this blade, that is called the viral component of the velocity. That is called the viral component of the velocity, okay. That is called the viral component of the velocity, and that is equal to v, sorry, that is your cw. And the perpendicular component which is along the radius direction, you can say, that is your radial component of the velocity, okay, or cr, okay. So this cw is very, very important, because when you are calculating the work, you are using this cw, okay. So how to calculate these things, and where are the angles, because all these magnitude of these components, these magnitudes you will calculate from the trigonometry, okay. So in trigonometry, what are the angles to be used, that should be very clear, okay. So with this note, I think we can stop here, okay. So I hope everything is clear. If there is any doubt, then please ask, and there will be one extra session. In that extra session, we will try to take your questions, and we will try to cover all the topics as much as possible, okay. So thank you for joining. See you in the next session.